In this video, we'll talk about higher order derivatives and how they can be interpreted in terms of a function. So the idea here is, since the derivative is a function, right, I take the derivative of some function to get another function back, well, I can just keep doing this process over and over again. So I can take that function that is f prime and take its derivative, and so on down the line, and keep going and going and going as many times as I want. So notation here, again, depends on whether you want to use Newton or Leibniz, but we'll go through both of them here. So I have a function f of x. Then with the following notation. The first derivative, also known as called the derivative, is written f prime for Newton's notation, or df dx for Leibniz notation. We can then go further. So if I want to take the derivative of the derivative, I then get to what's called the second derivative. And that's written f now with two apostrophes there, so f double prime of x, or d squared f dx squared. Watch where the 2's go in here. The reason why this is the way it is because this is the same thing as saying d squared dx squared, so two derivatives applied to f. That's what the notation is the way it is. You can continue. Third derivative, f with 3 marks, f triple prime of x, or d third f dx cubed. And this continues. Once you're beyond 3, you don't really make hash marks anymore. So the nth derivative for any number n is written f upper in parentheses n of x and dnf dx to the n. The point here is, once you get beyond 3 or so hash marks, it gets hard to read and see what's going on. So you just write the number n that you want in parentheses in the exponent to indicate that many derivatives of the function. As an example, let's let f of x be x cubed plus 2x squared minus 3x plus 1, and we want to find all derivatives. That means theoretically taking derivatives over and over and over again forever. We'll see in this case there's a pattern in the sense that they stop at some point. So what is f prime here? Our first derivative f prime is going to be 3x squared plus 4x minus 3. Then to get the second derivative, I want to take this function and find its derivative. And so that is going to be 6x plus 4. For the third derivative, I now take this function and find its derivative, which is going to be 6. For the fourth derivative, I do the same thing and I get 0. What happens from here on out? I'm going to always get 0. So f5 of x is also 0. And this continues. Fk of x is 0. For all k bigger equal 4. So I have a first derivative, second derivative, and a third derivative that are non-zero. Everything else is all 0, which will make sense because I have a third degree polynomial up here. So after 3 derivatives, it's all gone. It all just goes away because that's the highest degree I have in this polynomial, because I lose 1 power every time. And so once I do it 4 times, everything's gone. How can we interpret higher derivatives? In this case, the second derivative. So what is the second derivative? Well, it is the derivative of the derivative, which seems obvious. The derivative is measuring how fast things are changing, right? It's the slope of the tangent line. So this is saying how fast is the derivative changing? Well, in terms of linear motion, derivative here is velocity. So if I care about how fast the velocity is changing, that's just acceleration. So the second derivative in the case of linear motion is just acceleration. It's how fast is my velocity changing as I go around. On a graph, we're basically looking at how fast is the slope of the tangent line changing. So if I draw 2 graphs here, and assume they're on the same scale, which of these is going to have a larger second derivative? I'm looking at how fast the slope of the tangent line is changing. If I look at 3 points, say 1, 2, and 3, which will pair with 1, 2, and 3, for the graph on the left, my tangent lines look like this, and for the right, they look like this. Now, on which one is the slope changing faster? Well, it's the one on the right. Because for the one on the right, I go really steep, flat, and then really steep again, whereas on the left, it's sort of a gradual shift around here. If you look at functions that look like this would be something like this function being 1/4 x squared, and this function being 4x squared. If you look at second derivatives, this one's 1/2, and this one is 8. The second derivative models how fast these slopes are changing as you move along the curve. There's the idea of higher derivatives, how you compute them, and how you can sort of visualize them using either graphs of functions or the idea of linear motion and derivative being how fast something's moving over time.